Welcome to this tutorial on mastering fork and C. In this video, we'll break down the fork system call step by step, helping you build a strong foundation in system programming. We will cover key features like process duplication, separate memory space, execution paths, etc., all crucial for real world applications. Plus, we will tackle common interview questions and concepts like zombie process, orphan process, etc., helping you ace coding interviews. Let's dive in and master fork together. So, what exactly is a fork? It is a system call that creates a new process by duplicating the calling process. Fork creates a new process called the child process. After the fork call, there are two processes. The original is called the parent process and the newly created one is called the child process. Both processes execute the same code but operate independently. Let's see the basic example. Here is the example code that demonstrates the functionality of fork system call. Here we have called the fork system call and we have two prints. One is before fork and other is after fork. So can you guess what will be the output of this program? This program will print before fork one time and after fork two times. Can you guess the reason why? This is because when fork system call is called, there are two processes. This original one is the parent process and system creates a new process called child process. And hence this printf after fork will get printed in parent process as well as in child process. So after fork will get printed two times. Let's compile this code and see. Here as you can see after fork is printed two times. The fork system call is a fundamental concept in process creation. Let's explore its key features. First, process duplication. Fork creates a new child process that runs independently of the parent. Each process has a unique process ID. Next, separate memory space. Even though both processes start with the same memory content, they have independent copies. Modifying variable in one process does not affect the other. Third, different execution paths. After fork, execution splits into two paths. The parent receives the child's process ID while the child gets 0, allowing them to execute different instructions. And lastly, file descriptor inheritance. Both processes inherit the same open file descriptors, meaning they can access the same files. However, each maintains a separate file pointer offset. We will see examples of each of these in subsequent section. Understanding these key aspects of fork is a crucial for mastering process management in Linux and Unix based systems. One of the most important features of fork is that it creates a separate child process which gets its own unique process ID. Parent and child have unique process IDs. The child process runs a copy of parent's code but executes independently. We can check this by printing process IDs. Let's understand with the help of code. Let's understand the process duplication concept with the help of this code. Here we have called the fork system call and based on the return type we have two printfs. So can you guess what will be the output of this program? We have if else condition here. What will be the output of this program? Will both these printfs will get printed or only one? Can you guess? Both of these printfs will get printed. This is because fork returns two values, a child's process ID in the parent and 0 in the child process. Let's see the man page of fork to understand. Here as you can see, fork creates a new process by duplicating the calling process. The new process is referred as a child process and the calling process is referred as the parent process. Let's see what it returns. Return value. On success, the process ID of child process is returned in the parent and 0 is returned in the child. Let's compile this code and check the output. Let's run this. Here as you can see both printfs are printed. In this code, this getPID function gives the process ID of the calling process and getPPID gives the process ID of the parent process. So here the PID, first PID is the getPID. This is the PID of the parent process and the child PID is returned in this PID here in the parent process and which is 25737. As fork returns the 0 value in the child process, this else block will get executed in the child process. So this get PID gives the process ID of the child process. Here as you can see it is matching with this PID, and get PPID is the process ID of the parent process, which is this PID. Here important point to note is fork return two values, a child's process ID in the parent process and 0 in the child process. Another important feature of fork is parent and child processes do not share memory. Each gets its own copy of global and local variables. Variable changes in one process do not affect the other process. Let's understand this with the help of one code example. Here is the code to understand concept. In this code we have one global variable which has the value 10 and one local variable local var which has the value 20. Here we have called the fork system call to create a new process. This is just the error handling. Fork returns -1 in case of error. As we already know now, fork returns the 0 in the child process and child's process ID in the parent process. Hence, in this if PID equals to 0 condition, child processes code will get executed, and in else part, parent process code will get executed. So what will be the output of this program? Can you guess? In this child process, both variables are incremented by 5. So the modified global will be 15 and the local will be 25. And in the parent process, both variables are unchanged. There is no modification here. So the global will be 10 and the local will be 20. Do you know why this is the case? Let's understand it. So the moment fork system call is called, it creates a duplicate process called child process. So we have a child process and we already have a parent process. And both processes will have its own set of variables and memory space. So parent will have its own global variable and own local variables, and child will have its own global and own local variables. So any change in the child process or any change in the parent process will not affect other process. Let's compile this code and see the result. Let's run it. Here as you can see in the child process, modified global is 15 and local is 25, and in the parent process global is 10 and local is 20, which is unchanged because we have not done any modification in the parent process code. Another important feature of fork is both parent and child can execute different parts of the code. After fork, both parent and child can execute different instructions. As we have seen in earlier example, to execute different instructions after fork, we can use if-else condition. If PID is 0, we know that we are in the child process, and if PID is non-zero, then we know that we are in the parent process. This allows us to execute separate tasks in the same code. Another important feature of fork is file descriptor inheritance, which means both the parent and child inherit open file descriptors, meaning they can write to the same file. However, they do not share the file offsets. So the order of writes may be unpredictable. Let's understand this with the help of code. Let's understand file descriptor inheritance with the help of this code. Let's open a test.txt file for writing. Let's call the fork function to create a child process. So within the child process, let's write child to the file, and within the parent process, let's write parent to the file. So what will be the output of this program? After running this program, what will be the content of this test.txt file? Let's compile this code and see. Let's run it. Let's see the content of test.txt file. Here the output is parent and then child, but this output is not predictable because both processes will have their own independent file offsets. The write can be unpredictable. Now let's tackle some of the most commonly asked interview questions related to fork. How many times does fork return? As we already know by now, fork returns twice. Once in the parent process, fork returns child's process ID in the parent process, and once in the child process. In the child process, fork returns 0. How do parent and child communicate? Parent process and child process can communicate using inter-process communication, that is IPC methods. What are those methods? Number one, pipe. It is a unidirectional data transfer method. Message queue. It allows structured data exchange. Shared memory, it is the fastest method. And using signals, a simple notification related method. We will learn each of these methods in great detail in a separate video. What is a zombie process? A zombie process occurs when a child process completes its execution and the parent does not call wait. The child process remains in a zombie state until the parent reads its exit status. So a zombie process is a process that has terminated but still exists in the process table because its parent has not collected its exit status. This happens when the parent doesn't call wait function, causing the child's resources to remain allocated. Let's understand the zombie process with the help of one example and let's see how to spot them. This code demonstrates the zombie process. Let's create a child process by calling the fork system call. In the child process, we will just print the child process ID, and once it is printed, it is going to directly exit. And in the parent process, if you notice carefully, we are not calling any wait system call. Parent process does not call any wait, so the child will remain in a zombie state. Let's add one sleep of 30 seconds to observe the state. Let's compile this program and see the behavior. Let's run it. Now child has printed the child process and exited immediately, and parent is sleeping for 30 seconds. Let's quickly observe the state using ps command. This is the zombie process here. This is the parent process and this is the zombie process. In the ps command output, it is denoted by defunct, which means this is a zombie process. How to prevent orphan processes? An orphan process is a child process whose parent has terminated before the child finishes execution. In this case, child gets reparented to init process. This doesn't waste resources but can be avoided by making the parent wait for the child's completion. Let's see with the help of one example. Let's analyze this code to understand the orphan process. Here fork is called to create a new child process. So if PID is greater than 0, we know that we are in the parent process. Otherwise, we are in the child process if PID is 0. So in the parent process, we are just calling this printf and exiting the code. Parent process will terminate immediately after calling this printf. And in the child process, we are sleeping for 10 seconds and then printing this printf. Child process running PID and new parent ID. So we are printing the process ID of the child process and the process ID of its parent. So what should be the output of this statement? Any guesses? So this statement will print the process ID of the child process and get PPID will print the process ID of the new parent. Let's quickly compile this code and run. Let's run it. Let's run the ps command. Here, as you see, this printf has been printed here with the new parent PID of 4283. And what is that PID? Let's see in the PS output. This is the child process's PID, which matches with this PID here, 76876. Now let's see which process has this 4283 PID. 4283 is the PID of systemd process. In many modern Linux distributions that use systemd, when a parent process exits, the orphan child process is reparented not to the traditional init process but to the systemd process. Now that you understand fork, try modifying the examples and experiment with process management. If you found this video useful, don't forget to like and subscribe for more system programming tutorials. Thank you. See you in the next one.